Right now, at this very moment, we're all swimming in a sea of invisible energy waves. They're coming from a vibrating guitar string, they're bouncing off canyon walls, and some animals, like bats, even use them to see in the dark. Today, we're diving deep into the science of sound. We hear things all day long, but have you ever just stopped and wondered what sound actually is? What's really going on in that invisible space between a speaker and your ear? Well, it's so much more than just noise. At its very core, sound is a wave of pure energy. So today, we're going to follow the incredible journey of a single sound wave, right from the moment it's born to its final destination inside your ear. Okay, so our journey has to start at the very beginning, right? Before we can follow this wave, we need to get a handle on what the wave actually is.
Think of sound as energy that's a little bit needy. It has to have something to travel through, a solid, a liquid, or a gas. It simply can't exist in a vacuum. That's why in all those sci-fi movies, the giant spaceship explosions should actually be completely silent. In space, there's just no medium for those sound waves to travel through.
Now, when you hear the word wave, you're probably picturing ripples in a pond, that classic up and down motion. But sound waves? They're a different beast. They're longitudinal waves. So instead of going up and down, the particles of air get squished together and then spread apart, vibrating back and forth in the same direction that the wave is traveling.
So, if a high-pitched whistle and a deep, booming drum are both just waves, what is it that makes them sound so completely different?
It all boils down to two key things. First is frequency. That's just how fast the wave vibrates. A really fast vibration gives you a high frequency, which our brains hear as a high pitch. And second is amplitude. You can think of that as the power or the intensity of the wave. A wave with a big amplitude, that's what we hear as a loud sound. All right, so we know what our wave is and what defines it. Let's get it moving and see how it actually travels through the world. How fast does it go? Well, the speed depends entirely on what it's traveling through. Sound absolutely rips through solid steel at nearly 6,000 meters per second because the particles are packed so tightly together. But in air, where the particles are all spread out, it's much, much slower. Just as a benchmark, in the air around us, sound travels at about 346 meters per second. This is exactly why you always see a flash of lightning several seconds before you hear the thunder. Light is just ridiculously faster. And even that speed isn't constant. Things like temperature and density can change it. For example, sound actually travels faster on a hot day than on a cold one, because the air molecules have more energy and can pass the vibrations along more quickly. Okay, now this is where things get really fascinating. Our journey is about to take us beyond the limits of our own ears. The world around us is filled with noises we can't even perceive. You see, our hearing is limited to a pretty specific frequency range, from about 20 to 20,000 hertz. But there's a whole world of sound above and below that. Animals like bats and dolphins are absolute masters of ultrasound. These are super high-frequency sounds they use to navigate and hunt in total darkness. And of course, we've learned to harness this power ourselves with technology like sonar. It works just like a bat's echolocation. A ship sends out a pulse of ultrasound into the water. That pulse travels down, bounces off an object like the seafloor, and returns as an echo. By measuring how long that round trip took, the ship can map out an entire unseen world below. And that idea of bouncing and reflecting brings us to a phenomenon we've all experienced. What happens when a sound wave runs smack into an obstacle in its path? You got it, an echo. It's simply our sound wave hitting a hard surface, like a cliff face, and bouncing right back at us. It's basically the same way light reflects off a mirror. But for us to actually perceive that reflection as a distinct, separate echo, there's a really important timing element. Our brain holds onto a sound for about 1/10 of a second. The reflected sound wave has to arrive after that tiny window has closed for us to hear it as a separate event. And what's cool is we can actually calculate this. Knowing the speed of sound and our brain's 0.1 second processing time, we can figure out the exact distance needed. And it turns out, for you to hear a clear echo, that reflecting surface needs to be at least 17.2 meters away. So our wave has been born, it's traveled through the air, it's even bounced off some walls. And now, it's arrived at its final and most important destination, the human ear. This is where the magic happens, where the mechanical energy of sound becomes a biological signal. The outer ear catches the wave and funnels it to the eardrum. making it vibrate. Those vibrations travel to a tiny, snail-shaped organ called the cochlea, which miraculously converts them into electrical signals. From there, the auditory nerve zaps these signals to the brain, which finally decodes them into what we experience as sound. It's just incredible.
So, from a simple vibration to a complex signal in our brain, we've followed the entire journey of an invisible wave of energy. We've even peeked into the soundscape that exists just beyond our senses. It really makes you wonder, doesn't it? What other invisible forces are shaping our reality in ways we can't even begin to perceive?